Hi, I'm Mr. Meyer, and this video is on phase change diagrams. There's two terms I'd like to introduce. One is kinetic energy, or KE, and that is the energy of motion. So my lips moving as I talk, I'm a person skiing down a hill, water flowing over or a waterfall. Those would all be examples of kinetic energy, energy of motion. Potential energy is energy of position. So think of water held back by a dam, or think of a skier on top of a hill before that skier goes down, or think of energy stored in the bonds of glucose. That would all be potential energy. So kinetic energy, we're going to look at some diagrams, and the kinetic energy changes are going to occur along slopes in this diagram. The potential energy, increasing temperature will mean that molecules move faster, which means an increase in kinetic energy. Potential energy changes are going to occur along plateaus. And to keep in mind, the potential energy of a gas is going to be greater than the potential energy of a liquid, which is greater than the potential energy of a solid for any pure substance. So let's just get this diagram a little bit better right here. And on this axis right here, I have temperature in degrees Celsius, and I start at -20 or -40 down here, and I'm going up to 120 degrees Celsius right here. Down below, it just says, over time, I'm adding heat. So I'm going to gradually heat this substance. I'm going to take ice at -20 degrees, is heated at a constant rate until it becomes water vapor at 120 degrees Celsius. And we're going to kind of just do a play-by-play of what happens. So we're at -20. The molecules are in the solid state. Okay, they're held together in a fixed position, but they are vibrating. As we raise the temperature, the kinetic energy increases. They vibrate more quickly because we're along the slope. But when it reaches zero, the temperature levels out. It's not a kinetic energy change anymore. They're not going to vibrate faster, but they're going to break their attractions in the solid state and try to separate or try to become a liquid. So there's attraction in the solid state. They're breaking that. It turns into a liquid. And this whole range as that is happening, if it's stirred well, should keep it at 0 degrees Celsius, which would be 32 degrees Fahrenheit. Once it's all liquefied, then the temperature should rise back up. 10, 20, 30, 40, 50, 60, 70 degrees, the molecules are sliding over each other faster and faster and faster till you reach to 100 degrees Celsius, where they can't slide over each other faster without separating or breaking away. Does it take energy to break away? Yes, but now we're along a plateau, and that's a potential energy change along this plateau as the molecules separate completely from each other, going from a liquid to a gas, where in a gas they're a lot farther apart. So as you approach from here, it's almost all liquid. As you get over here, it's almost all gas. And by the time you get to this point, it's all gas. Once it's all gas, then the kinetic energy can increase and the molecules will even move faster and faster as it's a gas. So just going back along the slopes down here, those are kinetic energy changes, and the molecules are moving faster or faster as you go up that slope or faster as you go up that slope. And along the plateaus, the energy is changing, but the temperature doesn't, because it's a potential energy change as you break the attractions of the solid state and go to a liquid, or as you take that liquid and separate the molecules going to a gas state. During this entire process, this system is absorbing energy. Look at this phase change here at 0 degrees from H2O solid plus energy goes to H2O liquid. It takes energy to do that. It takes energy to melt ice, for example. It's a change in potential energy. And in this phase change here, H2O liquid absorbs energy to go to H2O gas. That's why when you boil water, you have to add energy to do that. How does this look going in the other direction? So let's take a look down there, and we're going to start with water vapor, which is a gas at 120 degrees Celsius, and we're going to cool it gradually over time. So we're starting out with a gas, but the molecules start to move more slowly, and when you reach 100 degrees, it can't stay in the gas state anymore. We're removing energy, but the temperature doesn't change now. It condenses from a gas to a liquid. Okay, so it's losing potential energy along this plateau. Once it's all liquefied, now the molecules are going to start moving slower, 90, 80, 70, 60, 50, 40, and they're moving more slowly until you reach 0 degrees. And then what happens? The kinetic energy stops. It's not going to move any more slowly, but now these molecules are going to start to connect together and again form these bonds like in the solid. So the waters are going to attach together in more of a crystal thing, forming those bonds between other water molecules. Once it has all frozen, then it can vibrate slower and slower as the temperature drops, and that would again be a kinetic energy change, except this time losing kinetic energy. So looking at this phase change up here from gas to liquid, it loses energy when it goes from gas to a liquid. Okay, you think about a storm, what happens? The clouds condense, form a liquid, gives off energy. That's often the energy to drive the storm. This one seems a little bit more unusual. H2O liquid, when it freezes, actually releases a little bit of energy. Sometimes when there's going to be a soft freeze, like one a little bit below the freezing point, they might spray the fruit with water. The water freezes on the outside, gives off a little energy to insulate the fruit. But that would be a giving off energy process, just the opposite of what we saw before. So in summary, with these phase change diagrams, along the slopes, yes, the energy of motion are kinetic energy changes. So this slope, and this slope. And what happens is the higher the temperature means molecules move faster and faster because that reflects an increase in kinetic energy. Potential energy changes occur along the plateaus, here and here. Gases have the most potential energy, more than liquid. And liquids have more potential energy than solids. So as you go from solid to liquid, you're actually increasing potential energy. As you go from liquid to gas, you're increasing potential energy here. All right, thank you.